Perfect. Thank you very much, Ruben, for the invitation and the very kind introduction. So I'm going to talk about some recent work done under lockdown. So I'm hoping to use this as a kind of sanity check. So please ask questions. I'm grateful for any comments or criticisms. So I'll be talking about boundary criticality in the ON model. So let me remind you what boundary criticality is. So imagine you have some system which is critical in the bulk, perhaps described by a conformal field theory, and you want to study what happens near its boundary. For instance, you might want to study correlation functions of local observables near the boundary. And in general, the behavior near the boundary will be somewhat different from that in the bulk. For instance, the scaling dimensions of operators on the boundary, denoted by delta hat here, will be different from their scaling dimensions in the bulk. Another comment is that given a critical system in the bulk, the boundary is not unique. There can be more than a single boundary fixed point, and there can be non-trivial flows between those fixed points. Of course, which fixed point is realized in a concrete model depends on the details of the Hamiltonian of that model near the boundary. All right, so boundary criticality is a very old subject going back to classical statistical mechanics, in the 70s and 80s, but there has been some renewed interest in it lately. Part of the reason for that renewed interest, I believe, comes from the study of symmetry-protected topological phases. Remember, SPTs are gapped in the bulk, but they have non-trivial boundary states. Well, in the recent few years, there's been a lot of interest in what happens if one starts with an SPT with its non-trivial boundary and then drives the SPT through a phase transition. Does anything of the non-trivial boundary survive at the phase transition? So I believe Tarun Grover and Ashwin were some of the first to study this question, but there has been a lot of subsequent work and also work on related questions about gapless, so-called gapless SPTs. In fact, we heard a very nice talk from Ruben last week about this subject. So I'll actually come back to this problem later in my talk in a very particular context. But for most of my talk, I will actually be talking about classical StatMech models, not about quantum models. In fact, I'll be talking about perhaps the best known classical StatMech model, the ON model. It appears that something might have been missed about this model, about the boundary criticality of this model. All right, so classical ON model. So take a d-dimensional hypercubic lattice, place classical spins on the sides of this lattice, n-component vectors, and couple them like this ferromagnetically. All right. So we have the nearest neighbor coupling, Kij, and let me study a model with a boundary, and let me say that for spins in the boundary layer, the coupling K is equal to K1, and otherwise the coupling is equal to K. Okay, so then, well, in the bulk, there is a phase transition as a function of K, well, alternatively as a function of temperature, where the bulk goes from disordered phase at high temperature to an ordered phase at low temperature. Okay, so that happens at this K equal to Kc. Now, let's study the boundary behavior. Well, the boundary behavior, the boundary behavior depends on the value of surface coupling K1. If the surface coupling is not too large, then the boundary orders at the same point as the bulk, at the bulk critical temperature. And this type of boundary criticality is known as the ordinary boundary, criticality. However, if we make the surface coupling K1 large enough, then it is possible for the surface to order before the bulk orders. So then we go into a phase with finite surface order, finite long-range surface order, but no bulk order yet. And then as we further lower the temperature, the bulk orders in the presence of an already ordered surface. So this criticality, this transition, ordering of the bulk in the presence of an already ordered boundary, is known as the extraordinary transition. And then, this multi-critical point separating the ordinary class and the extraordinary class is known as the special transition or special fixed point. Notice this kind of generic phase diagram. This is when dimension, the bulk dimension of the system D is greater than 3. So in this, if dimension is greater than 3, then we can have long-range surface order. Surface is D minus 1 dimensional, so it's greater than 2 dimensions. All right, so this few more comments. This green transition, the surface transition, is not very interesting. It's just a D minus 1 dimensional transition in the ON universality class, right? Here the bulk is disordered, so we can integrate the bulk out, just focus on the surface, we just get a D minus 1 dimensional transition. So the interesting boundary criticality is really along this line at bulk critical point. All right, so this is the situation when dimension is greater than 3. One more comment. So far, I've assumed that there is no explicit symmetry breaking field, either in the bulk or in the boundary, but one can also add an explicit symmetry breaking field to the boundary, H1 here. And in this case, there is just one universality class for the boundary transition. It's known as the normal universality class. Now, an interesting fact is that if the bulk dimension is greater than 3, then effectively the extraordinary transition here is equivalent to the normal transition. That is, it's not important whether the symmetry on the boundary is broken explicitly or spontaneously. Once we have a finite expectation value of the order parameter on the boundary, then it's really the same universality class. This is most obvious for the case of Ising spins, where, really the surface order is quite rigid, but it's also believed to be true for the case of n greater than 1. It's believed that the Goldstone modes of the surface, of the ordered surface, essentially decouple at this extraordinary transition if the bulk dimension is greater than 3. Okay, so this is the accepted lore. Any Any questions at this point?
Just to make sure, so at the extraordinary transition, you still have long-range order along the boundary. That is always true?
That is correct. Yeah, in dimension greater than 3, when there is a phase with true long-range surface order and no bulk order, as you approach the bulk transition, there is a finite surface order parameter, and it remains finite, and maybe it has some kink at the extraordinary transition, but yeah, it's finite.
Okay, thank you.
Any other questions? All right, very good. Let's continue. So let's now come to the question: what happens when the bulk dimension d is equal to 3? So surface dimension is 2. This is the question that will be really the subject of my talk. Okay, so what happens? Well, if we are dealing with Ising spins, if n is equal to 1, then the story is the same as I've just described in dimension greater than 3. However, things become more interesting when n is not 1. So let's first discuss the case when n is equal to 2. Okay, so what changes when dimension is equal to 3 and n equal to 2? XY universality class. Well, now, by Mermin-Wagner theorem, as long as the bulk is disordered, we cannot have true long-range order on the boundary. We can only have a quasi-long-range order. And indeed, if the if the surface coupling K1 is large enough, we will have a phase where the surface has quasi-long-range order and bulk is disordered. The transition into this phase is from lowering temperature is just classical 2D XY transition that is of Kosterlitz-Thouless type. Okay, so we have this surface phase with quasi-long-range order. Now the question we'd like to ask: what happens as we go through the bulk transition? What happens as we go through the bulk transition from the surface phase with quasi-long-range order? That is, what happens at this? I still call this the extraordinary transition. What happens at this extraordinary transition? And surprisingly, to my knowledge, it appears that this question has not been settled in the literature, either analytically or numerically. Really, the only
question.
Yes.
What do the correlation functions look like in that region where we have quasi-long-range order on the surface and the bulk is not? Where the cursor is. What do the correlation functions look like?
Well, if it kind of depends on the order of limits, right? So
I'm sitting at that point where you point the cursor.
Yeah.
And separating points very far.
Yeah.
Both on the boundary and away from the boundary.
Right. So if you take 2 points on the boundary, then you have power law decay as a function of boundary separation. Now I think you are asking what happens if you take those points away from the boundary into the bulk.
Yeah, but not too far. So
I believe you kind of have an exponential profile.
Imagine I separate them parallel to the boundary. So I can go to the boundary, then use the power law there, and then go back away from the boundary. So the formula should be a little bit more complicated.
Well, exactly. So let's say z is the distance to the boundary of the 2 points, and rho is the separation along the boundary.
Yes.
So I think you will have something like exponential of minus z over xc, where xc is the bulk correlation length, and then times 1 over rho to the power.
Thank you. That makes sense. Thank you.
All right.
Probably should be an exponential decay in both z1 and z2, right?
That's right. I took them to be the same distance from the boundary, but you can. Other questions? All right, so what happens at this extraordinary transition for n equal to 2? The only discussion of this that I could find in the literature is in this numerical paper, Monte Carlo study by Deng, Blotta, and Nightingale. And they suggest the following scenario. They suggest that even though there is no true long-range order above the bulk Tc, they suggest that exactly at the bulk Tc there is a true long-range order. That is, there is a jump of the boundary order parameter from 0 above the bulk Tc to a finite value at Tc, and then presumably stays continuous. All right, so this is kind of an interesting scenario, and I couldn't immediately shoot down this scenario because indeed, while when the bulk is disordered, there cannot be true long-range order on the boundary. At the bulk critical point, effectively the fluctuations in the bulk induce power law interactions of the order parameter on the boundary, and we know that if you have power law interactions in a 2D system, then we can get a true long-range order. Norman-Wagner theorem does not directly apply. So I couldn't immediately shoot down this scenario. Furthermore, the numerical study, the Monte Carlo data, was roughly consistent with this scenario. So as I'll show, this actually does not happen. This is not what happens. There is no true long-range order at the extraordinary transition for n equal to 2 in 3 dimensions. Rather, what happens is that at this extraordinary transition, if you look at the 2-point function of the order parameter on the boundary, it decays as a power of a logarithm of the separation of the 2 points along the boundary. And this exponent q, the power, is some universal number. So the boundary gets very close to having a long-range order along this extraordinary line, but does not quite have long-range order. Another fact that I find is that as you approach this extraordinary, as you approach bulk Tc, the Lagrange parameter of the surface diverges logarithmically. If it diverged as a power law, then you would end up probably with true long-range order along the extraordinary line. But because it diverges only logarithmically, you don't quite get that. So I refer to this behavior as the extraordinary log universality class. Okay, and these conclusions are based on RG analysis that I will explain later. Now let's ask what happens as we take n in the ON greater than 2. By the way, I will often be treating n as a continuous real parameter. Of course, most integer values of n are most interesting, but often I'll think of n as a continuous parameter. Okay, so if n is greater than 2, then we know that above the bulk Tc, we cannot have either true long-range order or quasi-long-range order. We must have a finite correlation length. So then the topology of the phase diagram does not mandate the existence of a separate extraordinary fixed point. It is possible that you only have the ordinary transition for n greater than 2. On the other hand, it's also not ruled out that you have a region of the phase diagram with a different universality class from the ordinary universality class. even though these connect really to the same phases away from the bulk TC. So then the question is, well, which one of these two scenarios is realized? And again, it seems that this question has not been addressed in the literature. I think the thinking at the back, kind of between the lines, has been that when n is greater than 2, you have the situation on the left with just the ordinary class existing. However, at least if you treat n as a continuous parameter, what I will show is that which one of these two situations is realized depends on the value of n. Turns out that as I'll show, that if n is large but finite, we only have the ordinary transition. However, if n is slightly above 2, we do have the extraordinary universality class with, the extraordinary log universality class with correlation functions of the order parameter on the boundary decaying as a power of logarithm of separation, and now this power q depends on n. So this is what my RG analysis indicates. So there are, even without a detailed RG analysis, there are reasons to believe that this is the case. First, let's start with a situation when n is large. Well, we can do standard large n calculations, and what we find is that when n is equal to infinity and the dimension is equal to 3, we find that there is no special fixed point. Okay, so there is no special fixed point, so that points to the fact that there is only the ordinary fixed point in 3 dimensions when n is infinite. Furthermore, we can study what happens as we take the limit d going to 3 from above. Right? So whenever dimension is greater than 3, as I told you, this is the accepted phase diagram with ordinary, special, and extraordinary fixed points, and these fixed points can be accessed in large n expansion. So in particular, we can go to the special fixed point, study it with large n in arbitrary dimension d, and then we can take d to 3. And there are results from the ages due to Ono and Okabe for, say, the scaling dimension of the boundary order parameter at the special fixed point in the 1/n expansion. Okay, so this, there is some long formula as a function of dimension d. If you take d equal to 3 plus epsilon with epsilon small, then to leading order, this is what you get. You get something that's proportional to epsilon, plus 1/n squared corrections that have not been calculated. But at least these first two terms suggest that as epsilon goes to 0, the scaling dimension of the order parameter on the boundary at the special fixed point goes to 0. Well, when scaling dimension of order parameter is 0, that means that it has true long-range order, right? So what this suggests is that as epsilon goes to 0, the special fixed point approaches the extraordinary fixed point, and then when d is equal to 3, they annihilate. And this is precisely the picture that my more detailed renormalization group analysis confirms. When n is large but finite, the extraordinary and special fixed points annihilate as dimension d goes to 3. Questions? Now, let's study the opposite limit. Let's discuss when n is slightly above 2. So we know that when n is equal to 2, we have the extraordinary fixed point. Well, as we'll see, it's of the extraordinary log type. Now we ask, well, what happens if we make n slightly larger than 2? Well, in general, fixed points do not disappear on their own. The way that fixed points disappear is they collide with other fixed points. Well, what are the other fixed points here? Well, there is the special fixed point, but that's some distance away from the extraordinary log fixed point. We know that the special fixed point from Monte Carlo, there are true power law correlations there with a finite exponent. So it's some distance away from the extraordinary log fixed point. So we expect then, as we make n slightly larger than 2, the extraordinary log fixed point should survive. All right. So then the interesting question is what happens in between these two limits? How does the system evolve? But first, let me sketch the RG analysis, and if I have time, then at the end of my talk, I will give a more detailed description of the RG analysis. But let me first give you the flavor. All right. So suppose we go to the region with a large surface coupling K1, right? So then there is a very strong tendency on the surface for the spins to locally order. So let me describe the spins on the boundary with a nonlinear sigma model for the boundary order parameter n. All right, this is the nonlinear sigma model. And for a moment, let me ignore the coupling to the bulk, and let me remind you what happens if you just have a two-dimensional nonlinear sigma model. Well, Polyakov has taught us what happens if we do perturbation theory around the ordered state, that is around g equal to 0. Then we have the following flow of the coupling constant g, which is a runaway flow away from g equal to 0. So this is what happens strictly in two dimensions. This is interpreted as saying that, well, in two dimensions, the nonlinear sigma model is disordered. Now, what happens when we include the coupling of the surface to the bulk critical modes? So what turns out to happen, as I find, is that this RG flow is modified. In particular, the coefficient of the g squared term that I call alpha here is modified. This is the old contribution. This is the extra contribution from the coupling to the bulk. So then the physics depends on the sign. I should say that this S is a universal number that depends on number of flavors n, and that actually is determined by certain universal amplitudes at the normal fixed point. Remember the normal fixed point? That's when you apply a field, symmetry breaking field on the boundary. So S is determined by some data of the normal fixed point. If I have time, I'll elaborate on that towards the end of my talk. But for now, S is just some universal number that depends on n. So, all right, so the physics then depends on the sign of alpha. If alpha is positive, then G runs to 0 logarithmically, and this is the extraordinary log fixed point that I talked about. You can easily show, the anomalous dimension of n is not modified to this order by the coupling to the bulk, and then if you take this anomalous dimension, combine it with the flow of g, then you find that as long as alpha is positive, then the correlation function of n has this behavior that it decays with power of log of the separation, and the power is expressed in terms of n and alpha. So this is exactly the extraordinary log fixed point that I sketched earlier.
Just to make sure.
I have a very naive question, if I may.
Okay.
What's the theory in the bulk? It's three-dimensional ON,
Yes.
And it's not renormalizable.
Well, you can use if you want, you can use phi to the fourth field theory. It doesn't matter. What matters is that the bulk is Wilson-Fisher fixed point for the three-dimensional ON model.
So, I'm sorry. So the bulk is 3 dimensions. How many dimensions of the bulk here?
3 dimensions.
And this is classical statistics. No.
Everything is classical.
Okay, thank you.
Can I ask about what about n equals 2? I mean, the Polякov recursion doesn't work for n equals 2.
The Polякov. Oh,
when n is equal to 2.
You're worried about vortices.
Yeah, I mean, you seem to be claiming this is valid for n2 and above, but I can believe it for n equals 3, but I'm not sure about n equals 2.
That's also true for n equal to 2, 2. Oh, let me make sure I see you. It's also true for n equal to 2. The leading order term in the beta function is
just 0, right?
0. Actually, all terms in the beta function, if you ignore vortices, are 0. So now I think you might be asking about vortices, and we can come back to that.
Okay, but the alpha term is, you can prove, exists even for n equals 2. The pi is squared over 2.
Exactly. I'll come to that in a second.
Just a simple question. So you were describing the log decay in the in-plane direction, right? At this fixed point, are there anything interesting happening at the z direction also?
Things are very similar to the, remember I said that when dimension is greater than 3, then the extraordinary transition is the same as the normal transition, that is transition in a field. So this extraordinary log fixed point in d equal to 3 is again very close to the normal fixed point. It's kind of normal fixed point up to these logarithmic corrections.
I see.
So that's more or less what's going on. Other questions? All right. Good. So that's what happens when the sign of alpha is positive. We have the extraordinary log fixed point. What about, when alpha is negative, then g equals 0 is unstable. G runs away from 0, and we don't really know where it runs away. We will talk about that in a second. Okay. Now, what is the sign of alpha? There are 2 limits where we know the answer. First of all, when n is equal to 2, this term coming strictly from 2 dimensions is 0. We only have the contribution from the coupling to the bulk. S is a real number, so s squared is positive. So when n is equal to 2, alpha is positive, we have the extraordinary log fixed point. On the other hand, when n goes to infinity, one can compute s in the large n expansion. This is what you get for alpha. So when n is large but finite, alpha is negative. So that means that alpha must change sign as we dial n from 2 to infinity, must change sign at least once. So let's assume that there is the simplest scenario that it changes sign once at n equal to nc. What is the value of nc? I think it's fair to say that we don't know. If we just take this large n estimate and try to extrapolate, we would conclude that nc is something like 4. One can combine the large n with some bootstrap data. If I have time, I'll comment on this, and that gives nc close to 3. But I think, at this point, we really don't know what the exact value is. Almost certainly it's not an integer, it's some real number. Okay, so what happens what happens near this critical value NC? How does this evolution take place? Well, there are two scenarios. Really, near NC, the physics will be determined by a higher order term in the beta function. The leading order term, this alpha term, we can linearize around n equal to nc. And well, the sign is determined. But the sign of this subleading term we don't know, because there are also, if it was only a matter of the surface, we would know, but there are also bulk contributions to this higher order term, and we don't know the sign of those contributions. So let's consider both cases. Let's start with a case when B is positive. So in this case, if we take n slightly below nc, we find an infrared unstable fixed point at a perturbatively accessible value of the coupling constant g. So we identify this fixed point with the special transition, separating the extraordinary log phase and the ordinary transition. Remember, this special transition exists as n equal to 2, so we just guess that it continues all the way to nc. Near nc, the special transition becomes perturbatively accessible, and then at n equal to nc, the extraordinary log and the special fixed points collide and annihilate. Then for n greater than nc, we only have the ordinary fixed point left. This is the scenario when b is greater than 0. It's perhaps the more conventional, the less exotic scenario. A more interesting scenario is that b is less than 0. If b is less than 0, then what you find is as you take n slightly larger than nc, the extraordinary log fixed point moves away from g equal 0 to a finite value of g. So it becomes you get an infrared stable fixed point at a finite value of g. That's perturbatively accessible. So at this fixed point, we now have correlation functions of the order parameter on the surface decay as a true power law with a small power, becomes small as n goes to nc. So I refer to this universality class as extraordinary power. Now we know that when n is equal to infinity, we only have the ordinary fixed point. So that means that as n further increases away from nc, the extraordinary power and the special fixed points have to disappear at some point. So we guess that there is a further critical value nc2, where the extraordinary power and the special fixed points collide and then annihilate. We again left with the ordinary fixed point for n greater than nc2. So this is the second scenario. It's less minimal than the first scenario, but ultimately, it's determined by the sign of b, and we don't know what the sign of b is, so I think we should keep both scenarios as viable at this point.
Alex, can I ask you a question? So, no, actually in the previous, yeah. So in the middle dashed line, so as you decrease G, I mean, at the high temperature, you have ordinary, but then at very low temperature, you have the ordinary boundary transition as well. Is it clear what that is?
Is it this?
No, to your left. I think this one is the usual one. Yeah, further left. Yeah, this extra, yeah.
Right, so you're thinking about n greater than nc and smaller than nc2, is that correct?
Yes.
And, well, I'm claiming that there is still an extraordinary transition here, but instead of having correlation functions that decay as a power of log, they decay is just power of separation, so it's more conventional. Maybe the next slide will make it more clear. So here's another way to look at the phase diagram in the two scenarios. In scenario 1, we have for n smaller than nc, we have the ordinary region and the extraordinary log region. As a function of the surface enhancement, there is a special transition separating them, and then, well, for n greater than nc, we only have the ordinary left. In scenario 2, the extraordinary log fixed point first evolves into the extraordinary power fixed point for when n is greater than nc, and finally disappears when n is greater than nc2. Hassan, does this answer your question?
Yeah. I thought the upper purple line is kind of tilted, but yeah, it's straight. Okay, got it. Yeah.
Any other questions? All right. So this is basically the story. Now, there is not much more I can say analytically. So let's turn to numerics. Does numerics tell us anything about which of these two scenarios is realized and the critical value NC? Let me first discuss classical Monte Carlo. Turns out there is actually quite little classical Monte Carlo for n equal 1 Ising case, we understand, at least the topology of the phase diagram we understand. N equal 2, again, we understand the topology of the phase diagram. N equal 3, we don't know whether 3 is here or here or here or here or here. Yeah, so we need input from Monte Carlo. So there is actually very little classical Monte Carlo studying, trying to study what happens at a significant value of the surface coupling K1. I only found two papers discussing this. Well, the first paper by Krech here, what they find is that, well, when the surface enhancement coupling is not too large, there is the ordinary universality class with rather well-defined exponents. But when the surface coupling becomes largish, they claim that they see exponents on the boundary that actually flow with the value of the surface coupling, which they interpret as a long crossover towards ordinary universality class. However, this subsequent paper by Deng, Blotte, and Nightingale that I already mentioned also looked at something like the Binder ratio for the surface order parameter, and you see that there is, in this Binder ratio, there is kind of like a crossing as a function of the surface enhancement. So this crossing is suggestive of a special transition. There is a special transition at this critical value of kappa. But the fate of the phase with a large surface enhancement of coupling is also not clear in this data. So I find it very surprising that in 2020 we still don't know what boundary criticality of classical O3 model is. I hope this will be studied in more detail. Surprisingly, there is actually more quantum Monte Carlo data. So there are a number of fairly recent papers studying 2 + 1 dimensional quantum spin models with, spin, so n equal 3, SO3 symmetry. And these models have the following form. Actually, the geometries studied are somewhat different in in these papers. Let me focus on the geometry studied in the papers by Stefan Wessel and collaborators, these last 2 papers. So let's take a rectangular lattice, and let's consider a Heisenberg model on that lattice. And we modulate, we have nearest neighbor coupling of the spins, and which is antiferromagnetic, and we modulate it in the following way. We make the coupling on these red bonds JD, and the coupling on the black bonds J. So the phase diagram of this Hamiltonian in the bulk is well known. When JD is large, then the spins on the red bonds lock into singlets. We have a paramagnetic phase, gapped. When JD is equal to J, that's a Heisenberg antiferromagnet on a square lattice. We know that that has Néel order. So then, as a function of JD over J, there's a phase transition from a Néel ordered phase to a disordered phase in this model. It turns out to be continuous and described by the O3 universality class in the bulk. It's quite well established numerically, no surprises there. The interesting recent new findings relate to the boundary behavior of this model. And there are 2 types of boundaries that have been considered. One is called the non-dangling boundary. So that's the top boundary here. So here the boundary spins a part of the strong JD bonds. And then there is the dangling boundary, where the boundary spins a part of the weak J bonds, of the black bonds. And well, for the non-dangling boundary, the critical boundary behavior found is consistent with the ordinary universality class seen in the classical StatMech models. Scaling dimension of boundary order parameter is something like 1.15, 1.2, which is the scaling dimension which is seen for the ordinary universality class in the classical O3 model. However, for the dangling edge, a rather different exponent is seen, exponent which is closer to 1/4. So, okay, 1/4 is quite different from 1.2. So I think, and basically all the 4 papers that I listed here agree on this exponent. So this behavior at the dangling edge is quite interesting, and yeah, I believe is not entirely not understood. So the first set of models that were studied had spin equal to 1/2. You can study this model for any value of the spin, but the first set of models studied had spin equal to 1/2. And well, if you have spin equal to 1/2, then let's go to the paramagnetic phase, right? Let's make JD very, very large, right? So these red bonds lock into dimers, but you have a dangling spin 1/2 at the boundary here. So you can kind of think about this as in that case, you can think about the paramagnet as a stack of Haldane chains with spin 1/2 dangling on the boundary, and you should really then think about the paramagnet as a weak SPT protected by spin rotation symmetry and translation symmetry along the edge. So this is exactly the kind of transition I mentioned in my very first slide, where you have a transition out of weak SPT, and you might expect that maybe something of the non-trivial boundary of the SPT remains at the transition. Indeed, in this paramagnetic phase, right? Well, we have these dangling spin 1/2s on the boundary. We know that a spin 1/2 chain is gapless, right? So even here, on the paramagnetic side, we have a gapless boundary with non-trivial power law correlation functions. So the universality class of the boundary at the bulk transition cannot be just ordinary universality class. For the ordinary universality class of the classical O3 model, if you go on the paramagnetic side, nothing interesting happens on the boundary. There is just short range order. So something different must happen for this dangling edge in the case when S equal to 1/2. Perhaps not so surprising. The really surprising finding, at least for me, was that when people repeated Monte Carlo simulations for S equal to 1 rather than S equal 1/2, they found very similar exponents to the case with S equal 1/2.
Max, can I ask you a quick question?
Uh-huh.
Maybe it's not so relevant because, as you already said, it's not particular to spin 1/2. But nevertheless, if we think about this weak SPT edge mode, as you were doing, right? So if the SPT were in the other boundary phase, right? Say it spontaneously breaks translation symmetry, just like in the J1, J2 chain, that would presumably also affect in the hypothetical scenario where that edge mode is related to the boundary criticality, would you then expect a different boundary criticality, or do you think that same boundary criticality can be perturbed towards both edge modes?
Very good question. So it is possible that the boundary dimerizes, right? So if the boundary dimerizes already in the paramagnet, and then you go through the bulk transition, presumably that's just going to be the ordinary universality class plus a valence bond solid order on the boundary. And you could say, well, maybe that's the generic thing. Maybe always when you approach this bulk critical point, the boundary dimerizes. But there is no signature of that in the numerics. There is no signature of the boundary dimerizing in the numerics. Other question?
I am trying to mention kind of, it sounds like maybe a little bit of analogy that, consideration which were recently discussed about Majorana fermions in two-dimensional field theory, where you have, say, non-abelian theory in 2 dimensions, but also has this Majorana fermions, and comparison between fundamental versus adjoint fermions, Majorana fermions. And again, there is a kind of analogy between both two cases. I mean, the confinement, deconfinement for adjoint looks similar to fundamental. No, I mean, okay, just. I
see. Interesting. Yeah, maybe I don't know those results. Maybe we could discuss.
The most recent paper was by Karmagotsky and the collaborators on this.
Oh, okay. I'll look into it. Thanks. So to me this was very surprising, and I think this requires an explanation. So let me sketch a scenario which might explain this numerical observations. So first of all, let's remind ourselves in field theory, just in 1 + 1 dimensions, what is the difference between spin 1/2 and spin 1? Well, Haldane taught us what the difference is. The difference is, well, at least in terms of the nonlinear sigma model description, the difference is in this topological theta term. For S equal 1/2, theta equals 0. For S equal 1, for S equal 1/2, theta equal pi. For S equal 1, theta equal 0, modulo 2 pi. But as I said, this is a topological term. So this topological term is not seen in any kind of perturbation theory around the order state, in perturbation theory around g equals 0. So perturbative beta function is the same for any value of theta. So let's remember that. So now remember the RG for the boundary criticality of the classical ON model. Remember we had those two scenarios depending on the sign of the coefficient B. So let me assume that the second scenario is realized, right? So in the second scenario we have this region where we have the extraordinary power fixed point. And let me assume that the value n equal 3 lies between NC and NC2, right? So that 3 is somewhere here. That is that for 3 there is an extraordinary power fixed point. Furthermore, let me assume that 3 is close to NC, such that this fixed point is perturbatively accessible for n equal to 3, right? It lies at a small value of g. All right. So I can calculate, for instance, the scaling dimension of the boundary order parameter at this extraordinary power fixed point, and well, numerically in Monte Carlo the scaling dimension is something like 1/4. So maybe 1/4 is small, and this kind of perturbation theory is justified. Another point is, again, remember the theta term does not affect perturbative beta function. So kind of if this fixed point is perturbatively accessible, then up to non-perturbative effects it's the same for theta equals 0 and for theta equal pi. That is the same for s equal 1 and s equal 1/2. So this maybe is the explanation why numerics sees the same exponents in the two cases. Another observation is that when n is close to nc, the crossover to scaling exponent at the extraordinary power fixed point is small, goes as n minus nc squared. So maybe that explains some of the flows of the exponents seen both in classical Monte Carlo, in the region with large surface enhancement, and also in quantum Monte Carlo. In the last paper by Stefan Wessel, they applied an explicit perturbation to the boundary and saw some variations of the boundary exponents. So maybe it's due to this small crossover to scaling, to this small omega. All right. So that's basically the story. Now you can ask, okay, what about those non-perturbative effects, distinguishing s equal 1/2 and s equal to 1? Well, those non-perturbative effects come from the theta term, and classically they're saturated by skyrmion configurations of the order parameter. Now, classical action of a skyrmion is like this: 4 pi over g times m, where m is the skyrmion number. So I would guess that if we have this perturbative fixed point at g star, then contribution of skyrmions will go like this: e to the minus 4 pi over g star. We should replace g by its fixed point value. Now if I replace, I can express this in terms of the scaling dimension of the boundary order parameter, and that's what I get. And if I plug in scaling dimension equal to 1/4, I have e to the minus 8. Okay, so maybe this is the large suppression. This is a small number, so maybe that's what's responsible for s equal 1/2 and s equal 1 having similar exponents. Of course, I cannot calculate the prefactor in front of here, so this should be taken with a grain of salt. Another comment. So far, I've focused on correlation functions of the Nel order parameter, the magnetic order parameter on the boundary. But there is another important operator, we know in 1D spin chains, is the valence bond solid order parameter. This is if I take the spins along the boundary, and I look at the dimers, and I look at the dimers at momentum pi. That's the valence bond solid order parameter V of x. Now, in the nonlinear sigma model, in terms of the quantum numbers of operators, V has the same quantum numbers as the Skerman density. Now, again, Skerman density is conjugate to the theta parameter. In perturbation theory, it's believed that theta does not flow, right? So if theta does not flow, then the scaling dimension of the Skerman density should equal to 2 up to non-perturbative corrections, the same corrections that distinguish s equal 1/2 and s equal to 1. So this is a prediction that the scaling dimension of the valence bond solid order parameter should be close to 2. Any questions? All right. Final comment. So I've sketched a scenario for this, that might explain the numerical observations at the dangling edge. And that scenario utilized this extraordinary power fixed point. Now, as Ruben was saying, we should be able to perturb the edge, so we should look at the phase diagram kind of more broadly, and the phase diagram at the dangling edge will depend on whether we are dealing with integer spins or half integer spins. For integer spins, we expect that the edge phase diagram looks like this. There is, at least in this scenario, there is the extraordinary power fixed point, there is the ordinary fixed point, and then there is a special transition separating those. Now, for half integer spin, as Ruben was pointing out, we cannot just have ordinary universality class. It must be accompanied by VBS order. In fact, if you go into the paramagnetic phase, starting with the extraordinary power fixed point, we should get the spin 1/2 Heisenberg chain, and this spin 1/2 Heisenberg chain cannot be trivially gapped. If it's not gapless, it must be dimerized. So there is the VBS phase here, and then presumably, if the bulk transition happens in the presence of boundary dimerization, then that's just an ordinary transition plus VBS order. So then, the special fixed point here is very interesting. We go from this extraordinary power phase to the ordinary fixed point with an simultaneous onset of VBS order. So this is a kind of deconfined boundary critical point. And actually, a theory of this critical point was discussed in a recent paper, was proposed in a recent paper by Xiaoming Zhang and Chenqi Xu. Really, the physics at this special fixed point will be different in the, both the topology of the phase diagram and the exponents presumably will be different for integer spin and half integer spin. And maybe in terms of our story, the way to think about it is, maybe the extraordinary power fixed point occurs at a sufficiently small value of the coupling G that the non-perturbative effects distinguishing s equal 1/2 and s equal 1 are small, but the special fixed point already occurs with large enough coupling that those non-perturbative effects are significant. All right. So I think these are all the qualitative things I wanted to say. Let me conclude by saying that I really hope, it seems that some things about the very old basic problem of boundary criticality in the classical ON model have been missed. And I hope that they will be studied in more detail numerically. I don't see why this problem cannot be slaughtered with classical Monte Carlo. Really, the open questions are which one of these two scenarios is realized and what is the value, the critical value NC. I think first thing to study numerically is the case n equal 3, but it should also, I suspect strongly that it should also be possible to study the problem as a function of continuous n by reformulating it in terms of loop models. So then one might be able to study this entire evolution. One more comment. I mostly talked about this extraordinary region. Now, the special transition is also interesting, and in the particular case of n equal to 2, one can make some progress on the special transition as well. Not for the classical O2 model, but for quantum models. In quantum models, like a Bose-Hubbard model, there is a free parameter, which is the excess boson density on the boundary, near the boundary. And when that density is incommensurate, one can actually completely understand this special transition from the extraordinary log fixed point to the ordinary fixed point. It's actually of a KT-like type, not exactly KT, but similar. So this is all the qualitative things I wanted to say. Thank you. If there is interest, I can take questions and then describe the renormalization group, the coupling to the bulk, in more detail for those who want to stay.
Thank you very much, Max, for a very interesting talk. Given time, maybe Dominic, you can stop the recording, and then we can just chat more. People can ask questions if they're